Photoelectric effect and solar energy. So we're going to talk about is what the photoelectric effect is and the impact it has on solar energy, because it's pretty much the precursor for it. It was created or discovered, if you will, by Albert Einstein. This is what he won the Nobel Prize for. And what he was able to show is that when you shine light on a piece of metal, you can make its electron get excited and jump from one location to the other. And as a result of that, you can actually have them travel to another location altogether. Basically, it showed that light can excite electrons. I mean, that's the long and short of it. But that little idea not only won him the Nobel Prize, but also helped us eventually figure out how to build solar cells. So here's some common uses of photoelectric effect: solar cells, smoke detector, security systems. If you've ever seen a movie where you have that laser light, the premise is basically based on the photoelectric effect. And when someone goes through, they stop the circuit of the electrons moving from one location to the other, and then that sets off the alarm. Smoke detector, similar principle. When smoke goes in there, what it does, it prevents the electron movement from one location to the other, and it triggers the smoke alarm. So what you're basically looking at is light hitting a surface. This is a piece of metal, and what's happening as a result of this collision is that you're able to have the electron get excited, or in this case, as it's referred to as emitted. This is another example. This is what Einstein's experiment basically was, this little glass tube on the right bottom side. He shined light on it, and what he's noticed is that he excited electrons, and he was able to verify based on the fact this electron jumped to this other location called an electrode, and what that did, it closed the circuit. And by closing the circuit, he was able to prove that basically you can make electrons jump with just light. So many metals emit electrons when hit with light. Sure, the wavelength, the greater the intensity of light that hits, the more electrons ejected. So if you remember, the relationship between short wavelength is high energy, right? So if you have something with short wavelength, you're saying high energy. So that means like blue and violet, which are more energetic than, let's say, red and orange. That's one way to impact the amount of electrons that are ejected, is the specific color or wavelength you use. Second thing is intensity. Intensity means how many times that photon of light is hitting the piece of metal. You could change that. It could be one little photon per minute, one per second. And as you vary that, that impacts what happens. So this is what you're basically looking at. Light hits the piece of metal. The metal has electrons. They're delocalized, which is a fancy way of saying they're not obligated to stay in one place. So when you hit them with light, you excite them, which you remember from quantum mechanics means you cause the electrons to jump to a different location. And in this situation, they're ejected as a result of this. So this is red light that's able to do this. Every piece of metal has a very specific wavelength of energy it needs in order to cause the excitation of electron, which is a fancy way of saying you have to have a minimum. So maybe one piece of metal, red works with it. Another piece of metal, red doesn't work because it's not enough energy. So the amount of energy is referred to as a threshold frequency. It's just saying the minimum you need to make this excitation occur. So down here, you can see that you have red being shot at this piece of metal. Now, this is potassium, by the way. You can see by the title right there. So red, no electrons are ejected. So what does that tell you? That 1.77 electron volts, which is what red produces or has, it's not enough energy to excite the electrons. Green, on the other hand, does. And it does cause excitation of electrons. And if green does, that means every color afterwards. So that means blue and violet will also cause excitation. They don't show orange, so you don't know if that will work or not. But you know at this point, based on the data, green is your minimum amount of energy you need in order to cause excitation of electrons. You can see different metals have different thresholds. So potassium is able to actually does work with orange. Sodium needs a minimum of blue. Zinc needs a minimum of green. Tungsten a minimum of yellow. And platinum, you can actually get away with red. So different substances have different minimum frequencies you need in order to cause excitation. And that's the important takeaway here, that not all metals are the same. Some require more energy, some require less. You don't have to memorize it, but just understand every metal has a unique amount of energy it needs to cause excitation. So in summary, correct wavelength of light will cause ejection of photoelectrons regardless of intensity. So whether you shoot 1 photon per second or 1,000 per second, as long as you have the right wavelength, you cause excitation of electrons. So intensity is the amount of electrons hitting at one moment. Whether it's 1 or 1,000, you're still going to get an electron ejected. Now, is it going to be as many electrons with 1 photon per second as 1,000? No. The more intensity you have, the more electrons, the more wavelengths of photons that are hitting, the more electrons that get ejected. Kinetic energy of photoelectrons depends on frequency of light used. This is basically telling you that the energy of these electrons being ejected depends on how much energy you use to get them out. So obviously, the more energetic the light you use, the more energy, kinetic energy of motion, those ejected electrons have. So for example, say the threshold is red and you use blue, then you could assume that the blue color that you use will have a higher kinetic energy electron being ejected than the one that was the red. Why? Because you're putting more in to cause the ejection. So the more you put in, the more you get out. Kind of story of life. There's a minimum frequency below which light won't kick out electrons, and that's once again your threshold frequency. But anything below that, nothing happens. So what is solar energy? So solar energy is basically sunlight being converted into energy. So here you see the different ways that light interacts with the earth, and here you can see a solar cell. So solar energy can be used as a source of heat, light, and can be used to generate electricity. So we know the heat component, right? I mean, that's usual. You could also get the light on a daily basis, but the part about using to generate electricity is not something that came about right away. It took many years after the Einstein's experiment to get to the point you're actually starting to use solar energy. And even now that you're using it, it's not super efficient, about 20% efficient, which means 20% of the light that hits it is actually converted to electricity. So in terms of efficiency, it's not all that great, but still, you are able to get electricity for free, more or less, right? Once you pay for the solar cells. So solar energy, main source of energy, with energy for plants, energy for us, fossil fuels, which are just stored products of photosynthesis. In case you know, when you're eating food, what you're basically doing, let's say you're eating a steak, the cow ate the grass, where the grass get the energy that allows the cow to survive, got from the sun. So sun is basically the origin of all life, right? Because if you don't have plants, you don't have any animals either. It's the cycle of life. So in the event that, something catastrophic happens and we're able to block the sun, you won't have any life anymore because the sun is that integral to life on Earth. So when you're eating grass or eating, not grass, when you're eating vegetables or when you're eating animals, you have to realize that energy source was always from the sun. Sun is the origin of everything. Amount hitting an object depends on season, weather, distance from equator, and what direction the object is facing. So if you ever put solar cells in your home, you'll notice that when they come out, they'll ask you which location you want, and then they'll tell you what the best location is because of the angle of the sunlight. So some locations are more efficient for tapping into photosynthesis than others, and that dictates everything. All right, using solar energy, photovoltaics, used to convert sunlight to direct current. So what you have here is a solar cell. When the light hits it, it will convert the sunlight into energy using the Photoelectric effect, basically, which you just saw earlier with Einstein's experiment, into electricity. But the electricity is direct current, and you probably wonder what that is direct current. Let's just say you can't use that at home. You need to have what's called an alternator, change that to what's called an alternating current. Without making this too, technical, let's just say what you get from sunlight is direct. What you need is going to be alternating. So there has to be something that causes that conversion. So here you can see sunlight hitting the object, which is basically composed of a bunch of solar cells, and then that's creating direct current, and that's what allows you to actually cause things to work. So a complete system needs an inverter. Remember, that's what converts the direct current into an alternating current. Power batteries to store energy. Ideally, you need like a capacitor that can store energy over a day. Right now, when you get solar cells, you're only able to really use them during the daylight hours because without sunlight, they don't function. But if you had a battery that stored the energy throughout the day, then what would happen is that you would be able to tap into energy at nighttime. So even if you do get solar cells, you're still going to be relying on the grid at nighttime unless you have a battery. So you would have to buy electricity from the city, obviously, at some point, unless you have a generator or something that could create electricity for you at nighttime when there's no sunlight and when it's cloudy. So here's the whole setup. First, you have the photovoltaic cells, which is basically an array of solar cells, a bunch of cells together. You have an inverter here at 2, which is what converts the direct current to an alternating current. You have some sort of breaker box that provides connection between the electricity you're generating and the grid being what the city is providing in terms of electricity. You have a separate meter. It's a whole process. You have to completely redo your whole home if you do switch into solar, because it requires a certain set of equipment to make it functional for you. Here's some examples of its use. This is used for medical buildings out in areas where it doesn't have electricity. These are able to generate electricity for it. Farmers use it for pumping water. So in areas that they don't want to go out to, they just want to have livestock, migrating about, they're able to generate enough electricity to cause these water pumps to work so the cows can drink water. PV cell, one PV cell produces 1 to 2 watts of electricity. So here we have a total of 12 of these in certain series. So theoretically, you could produce anywhere from 12 to 24 watts from this. Now, is it that efficient? No. It's going to vary depending on circuitry and other conditions. But when you have one set of these, it's called a module, and you have a whole bunch of these, we have an array. And that's what you put on top of your home, is an array. So to increase power, multiple cells used. Typically, you would need, let's say, anywhere from 6 to 12 arrays in order to generate enough electricity so that you're not reliant on the grid for your electricity throughout the day. Getting a few solar cells will still give you something. Obviously, you can save some money. But if you want to be energy efficient during the daytime when there's sunlight, you would need to have 6 to 12. In some cases, even more than that, depending on what your energy needs are. All right, just to show you what the rest of the world is doing in terms of using photovoltaic cells, you can see Germany, Italy, Czech Republic, 68% of all solar cells are used by them. So basically, Eastern Europe uses it a lot. Rest of the world is about 10%, Japan 6%. United States, you think would be higher, and we're getting better at it, obviously, but we're still not in the top. We're only at 7%. And the weird thing is this other year, 9%. The rest of the world includes the 2 most populous countries in the world, which is China and India, which has 1.3 billion plus each. And they are not even, in the neighborhood of Eastern Europe, which is interesting because if they convert completely into solar cells, then pollution would decrease drastically because they create a lot of the pollution along with us, obviously, because we throw a lot of junk into the air. Disadvantage of solar cells: 1, less efficient and costly equipment. You're looking anywhere from 20 to 25,000 to get enough solar cells so that you're not reliant on the grid during the daytime. And they're only 17 to 20% efficient. Now, there are commercial ones that are a little bit higher than this, 25 to 30, but they're really, really expensive relative to everything. And the bottom line for these is that you still, at some point, need to have technology that allows you to have what's called a capacitor or a storage unit for all the electricity that you generate in the daytime so that you can use it at nighttime. When you can do that efficiently, then you see solar cells really take off because now you really aren't reliant on the grid at nighttime as you are now. And in case you're wondering what happens to all the extra electricity you produce during the daytime, you sell it back at a fraction of what the city sells it to you. So go figure that out. Part times, it's only works in the day when it's not cloudy. Reliability depends on location. Some locations are better. The other things like trees and clouds impact it. And they're not cheap. Like I said, 20 to 25,000 is what you're looking at for a typical setup. And that is solar cells and photovoltaic cells.